Thank you all for coming. I know everybody's kind of busy with exams and it's a kind of busy time of the year, but this is the WIA technical workshop. And typically what WIA tries to do every year is have some sort of hands-on experience for students so they can sort of apply what they're learning in class into like a real world situation. Because, you know, how many times I've sat down in class and thought, when am I going to use this? So this is sort of an application of a lot of undergrad aero classes. This particular presentation, we're going to be talking about flight controllers. So stabilization of unstable vehicles that can go anywhere from UAS all the way up to, you know, full scale rockets, helicopters, anything like that. This all general theory applies. And of course, we're going to talk about, you know, how do you simulate this when you have a controller in the loop. And that's what the MATLAB component of this is going to be. Just about me really quick, I'm second year master's student with Dr. Chopra, and my research focus is rotorcraft and electric VTOL. So some of the things I'm doing are, you know, studying unique VTOL configurations. This is called a cyclocopter, and it basically rotates about this shaft here. Can you guys see my cursor, by the way? I'm not sure. But anyway, it generates thrust perpendicular to the axis of rotation, unlike a conventional propeller, which is pretty cool. This is it's called a quadrotor biplane. We recently designed this for a challenge, and it's about a 40-pound vehicle, and it can hover, but it can also efficiently fly like an airplane and carry a useful payload. And then more recently, I've been working on an open source flight controller package. So that's sort of my motivation for doing all of this today. I'll talk a little bit about this. We'll be using this later on the test stand to actually implement our controller. So today, the presentation, I'm going to talk about, you know, the application of a flight controller, why you might or might not need one, the inner workings, so, you know, how you input data and output data and why you're doing what you're doing. And then we're going to focus in on PID controllers specifically. So PID controller is just the way that you numerically calculate an output based on your measured error. And then finally, we'll hop into MATLAB. I'll show you guys how to do a simple Euler integration with a very simple example, and then we'll apply that to the test stand that I have over here in the other screen here. And we'll play around with this. We'll upload some controller gains to it and have some fun. Oh yeah, here's a picture of it, a little bigger. So why do you need a flight controller, or why do flight controllers exist? Well, you might not actually need a flight controller. So my first point here is, you know, if you need a flight controller to fly an airplane, you probably did something wrong. And this is something I had to keep telling my team when I was on DBF in 2019. They kept wanting to design an airplane that like required a flight controller to fly. And I'm like, guys, if you know, an airplane is supposed to be inherently stable. As aerospace engineers, we really want to try and design aircraft that want to stay in the air. So, you know, you take like a typical Cessna aircraft and you disturb it, it's going to naturally right itself. And that's good because it makes it easy to fly and it keeps it in the air. With that said, we still do see many vehicles that are inherently unstable, and they definitely serve their purpose, and we do that for a reason. But you know, you don't design an aircraft thinking that you're immediately going to put a flight controller on it. You know, multi-rotors are inherently unstable. They cannot fly without active stabilization. Rockets, you know, small rockets can be passively stable, but bigger rockets need active stabilization. Fighter jets, it's an example of you know, an airplane that should be inherently stable, but the designers actually make it inherently unstable by making the center of gravity way too far back. And that gives them some other advantages. Helicopters are inherently unstable. Sometimes you don't need a flight controller because a pilot can just take care of that, but you know, stabilization can help. So, you know, when I say stability, what am I talking about? Basically, if something is stable, that means when it's disturbed, it will not fall completely out of control, but rather settle into some steady state. And we can think about this like a marble in a valley here. A completely stable aircraft, or I guess completely stable system, will sort of settle down to this equilibrium point no matter what you do to it. So that's a stable system. Neutrally stable means, you know, if you push it, it'll just keep going at some constant velocity, which is also very controllable. There are many aircraft like this. Unstable is where we get into some trouble, where, you know, it's equivalent to a marble on top of a hill. And as soon as you give it a little nudge, it'll just start accelerating down the hill. And that's bad. So, you know, you can control an unstable vehicle, but it becomes uncontrollable when a human's reaction time is not fast enough to keep it stable. So that's sort of how we define, you know, the need for a flight controller. And helicopters are like this. Helicopters are unstable, very unstable. It's just that, you know, they're so big that a human can probably react fast enough to correct it. You know, why would you build an unstable aircraft? Well, of course, helicopters exist. There's other aircraft. So VTOL, we see the multi-rotors. They're useful for taking off in small areas and carrying payloads. Super maneuverability. This is a video of a little F-35 like model that I built over the summer. And basically this thing is so darn tail heavy that you cannot fly it without active stabilization. But because it's really tail heavy, it has extreme maneuverability. So you can pitch it back and you can hover it the wrong way and you do some crazy things with it. Efficiency, you might design an aircraft that is, you know, on paper, it's extremely efficient, but it, you know, for some reason the wing generates some weird moment that'll make it uncontrollable. But you want to maintain that efficiency so you can get long flight times, whatever. Stealth, the F-117 is inherently very unstable and it requires active stabilization, but the F-117 was not designed as an airplane. It was designed as a stealth. That's what it was for. So they had to figure out how to make it fly. Basically, you know, to sum up what a flight controller is doing, it's measuring some state of the aircraft and it's performing corrections to the controls of the aircraft to achieve some desired state. And that desired state comes from a pilot. And this process is called closed loop control. And we'll talk about what that actually looks like, what that loop looks like a little bit later. So if you have like a multi-rotor, this is just, you know, this is a stick with two motors on it, but that's basically what a multi-rotor is. And you have some desired state, which is level in this case, and you can measure some deviation, then you can apply a control correction to bring it to that desired state. So in the case of a multi-rotor, you would spin up the motor on the falling side, and you would spin down the motor on the rising side, and that would bring it back to the desired state. For like a rocket, maybe you want to keep the nose pointed into the incoming airflow. So you would measure that desired state with maybe a pressure probe, and then you'd apply a control correction to the motor gimbal, which would apply a moment on the vehicle, which would bring it to that desired state. And that's basically what a flight controller is doing. Of course, there's sort of a sub-function of a flight controller in the case that, you know, sometimes the controls on an aircraft are not very straightforward. So an example where they are straightforward is, you know, an elevator on an airplane. One control surface controls 1 degree of freedom. The elevator control surface controls the pitch. Easy. A pilot can easily control that. It's very intuitive. A non-ideal case is a combination of multiple actuators controlling each degree of freedom. So a quadcopter requires some pretty advanced mixing in order to stabilize and fly. So in the case of, you know, hover, you spin up all 4 motors. If you want to pitch up, you need to pitch up, or you need to spool up the front 2 motors and spool down the back 2. If you want to roll right, you need to spool up the left motors. So basically this sort of mixing, you know, if you gave control of each motor independently to a pilot and you said, here, fly this quadcopter, they couldn't do it. So a flight controller also kind of steps in and it does this control mixing, or control, it sort of decouples the control on the vehicle. And that's, you know, not just the case for multi-rotors, it's the case for every type of aircraft. Of course, there's exceptions where you don't need a flight controller, but you know, if you get really clever with your design, then you can achieve a very stable aircraft without the closed loop stabilization. And if you've seen these like toy helicopters with a flybar on them, this flybar basically gyroscopically stabilizes the rotor. Without it, this helicopter would not be able to fly. And that's just a clever mechanical design. This is something out of ModLab UPenn. And basically they've designed like this aerodynamic housing, sort of like a physical damper on the vehicle. So that quadcopter normally would not be able to fly unstabilized, but all they're doing is the control mixing, no active feedback. And then that sort of damping cage is stabilizing the vehicle. So that's pretty cool. You know, flight controllers can stabilize unstable vehicles, but of course you can stabilize stable vehicles like an airplane, a trainer type airplane. You might want to uncouple the dynamic couplings, which would be, you know, a roll input would be a pure aircraft roll. If you apply ailerons to a regular fixed wing aircraft, you're going to get some pitch and you're going to get some yaw, but a flight controller can sort of decouple that. And of course, disturbance rejection. So if you get hit by a gust, it can correct for that for you. But of course, you know, as aerospace engineers, don't get too blinded by this magic thing that'll make anything fly. You know, you still want to try and design an aircraft that wants to fly before you try and force it to fly with a flight controller. So keep that in mind. And you know, don't do this unless you really know what you're doing. Is what I'm trying to say. You know, an airplane is an airplane until you start getting crazy with it. And you know, quick note for the sake of this presentation. When I talk about a flight controller, I'm talking about like stabilizing a vehicle, how you keep it in the air. I'm not talking about like computer vision or autonomy or decision making. That's more like autonomous type operations, and we might touch a little bit on that. But if you're interested in those topics, I know a little bit, so you can email me. We can talk. So what are the inner workings of a flight controller? Flight controllers use feedback. And feedback basically means, I'm going to step through it here. You first measure where you are, you figure out where you want to be, and then you calculate a control output based on the error between those two. You give that output to the actuators, so your motors or servos. The vehicle responds, and then you repeat. That might sound familiar if you guys have seen this. This is the best aerospace meme that has ever existed. And when I talk about, you know, if you watch this video, I highly recommend it. It sounds crazy, but he's just describing this process. And you know, I mentioned autonomy. It all gets worse when the missile knows where you are. That's autonomy. That's not flight stabilization. Don't worry. So step one, you got to measure where you are, and you do that with an inertial measurement unit, or IMU. Inertial measurement unit has a couple of sensors on board. It'll have a 3 degree of freedom accelerometer, and this measures accelerations. So if it's sitting still flat on the ground, it'll be measuring 1 G, or 9.8 meters per second, in the Z direction. It also has a 3 degree of freedom gyro, and that's measuring an angular rate in degree or radian per second. And sometimes you might also have a magnetometer. It's not necessarily necessary for estimating attitude, but an important note is that none of these individual sensors can estimate your orientation in space. They can just give you data about your orientation. And the reason for that is the accelerometer it will tell you what down is, but its measurement is very, very noisy. So you cannot stabilize a vehicle off of that measurement alone. A gyro reading is very clean, but if you were to integrate the angular velocity measurement from it to get just an angle, because there will be sensor noise and sensor error, it's going to drift over time. So what you need to do is use sensor fusion, and that's when you combine all of these readings into one. You know, you can use a complementary filter, Madrig filter, Kalman filter. I encourage you to read up on these. They're very interesting. But basically, you know, you can take the very clean measurement of the gyro and integrate it to get an angle, but that's going to drift. So you can use the accelerometer that always tells you which way is down, and that can sort of correct it and say, okay, stop drifting, down is down. And that's why you need sensor fusion. And that can give you your orientation in space. So we've gotten our IMU data, we've fused it, and we're going to fill in this sort of block diagram here as we go. Next, you need to figure out where you want to be. And this is sort of where the pilot comes in. You can either stabilize on a desired angle or a desired angular velocity. And we call this an angle controller or a rate controller. You know, on full scale, this is I believe this is an F-18 control stick. You know, a full scale stabilized aircraft like a fighter jet, they actually design these control sticks to give like pilot feedback, which I think is pretty cool because they're not actually directly linked to a control surface anymore. So the design of these is really interesting. For UAVs, we use, you know, a radio system on the ground that talks to a receiver on the aircraft. So our pilot input gets thrown in here, and we get our desired set point, either the angular rate or the angle. Somebody's chatting here. Let me make sure everything's okay. Oh, yeah, I didn't realize there was a waiting room. Thank you. I think I have to stop the share really quick, but 1 second, guys. Um, oops. Okay, sorry. Thank you for that. Okay, so we've added our pilot input. We've gotten our desired set point, either an orientation or an angular rate. Oops. And next, we're going to step 3. We're going to calculate a controller output based on the error, and this is where we're going to kind of dig deeper later. But basically, the basis of this is, you measure an error, which is your desired state minus your measured state. And there's different methods to do this. ENA 432 with Dr. Sander, you'll talk about linear and nonlinear control theory, and this is sort of like a general way to create a controller for a known system. You're basically designing for what's called pole placement using eigenanalysis, and it's very, very tricky. It's an art form, pretty much. A little simpler type controller is called a linear quadratic regulator, which basically you take a differential equation which describes your system, and you find optimal control gains based on a quadratic cost function. And if these words scare you like they scare me, then you can just use PID control, proportional integral derivative, which it's a very simple, intuitive set of rules applied to each degree of freedom of the aircraft, and it works pretty well. So, these other methods definitely have their place, but if you just want to get something working, PID will help you out. Of course, we're talking strictly about stabilization. We're not talking about navigation, which is more the autonomy side. But what that might look like on an aircraft is you have your inner loop, which is your stabilization loop, stabilizing on a rate or an angle, and that loops around on your attitude. And then you can have an outer loop that loops around on your vehicle position. So the outer loop is basically telling the inner loop, hey, I want to go, to get from point A to B, I need to pitch forward. And it requests that from the inner loop. The inner loop says, okay, I'm being told to pitch forward. I'm doing that. And the outer loop just monitors that until it gets to the position it wants, or GPS coordinates. So we're talking about this inner loop. Of course, you can talk to me about this. We can nerd out if you want. There's a lot of interesting work being done here too. So we're going to add our controller, and this controller can be anything, but we're going to focus on PID later. The next step is to give the controller output to the actuators. So the first thing you need to do is after you've computed some output, you need to sort of scale it into an acceptable range for the motors or actuators, because saturation is a thing. And saturation means that you've sort of maxed out your control deflection. Now, you don't want a controller that's basically saying, like, I want my control surface either full up or full down. That would be a bad controller. So you need to sort of bring it into an acceptable range. You also need to mix them. We talked about the control coupling earlier. For a quadcopter, you need to make sure that the stabilized variables for each axis are being applied correctly to the configuration. And then you need to send them out to the actuators. So for UAVs, we use what's called pulse width modulation, which is just it's sort of like a digital signal, and you vary the duty cycle to tell the servos or motors what to do. Problem with this is, there's not a problem with it. It works well, but it's kind of slow. And with a controller, with a really small vehicle, you want the controller to be as fast as humanly possible. So recently, what the hardcore racing quadcopter guys have been doing is coming out with new protocols for talking to motors and servos, one shot, multi-shot, D-shot, and these are 100 to 1,000 times faster than PWM. And what that means is, as soon as you calculate a control output, it immediately gets sent to the actuator with no delay, and that'll give you a much better responding vehicle. So here's a diagram. We've added control mixing, and we've sent the outputs to the actuators. The only thing left is the actuators do their thing, and the forces, moments that they exert on the vehicle leads to a vehicle response. This vehicle response feeds back into step 1, and we've closed our loop. That's why it's called closed loop. So basically, you just do this as fast as you possibly can. For MAVs, you want to go at 1,000 hertz plus to get a really good controller. But full scale, things with much higher inertia, very sluggish vehicles, they're only about 50 to 100 hertz. So, but ideally you can go as fast as you possibly can. Of course, we can implement this sort of closed loop strategy on a microcontroller, and I'll talk about the PID implementation. But if you're looking for a hardware that can do this, it needs to be fast. So an Arduino microcontroller that that can run not just at 1,000 hertz, but typically you'll need about 18 megahertz because you're doing a lot of computations. So the actual loop rate of the flight controller should be very fast. You need your 6 degree of freedom IMU, the accelerometer and gyro that we talked about. You need some way to input pilot commands, either through your joystick, creating a digital signal that the microcontroller can read, or the receiver, decoding the receiver commands, and then sending the outputs to the motors and actuators, depending on what protocol they require. If you're working on MAVs, obviously you can see, we're talking a little bit more towards small scale drone technology, but Betaflight, ArduPilot, PX4 are pretty established solutions, and these are pretty standard across all UAVs that you see that are 20 pounds and under. And of course, if you're looking for a simpler bare bones solution, I've been developing this flight controller package, and it works out of the Arduino environment. Basically, these guys have a bunch of spaghetti code that's really hard to understand if you're not a comp sci major. Mine is like, okay, a student that barely knows MATLAB wrote a flight controller. So now we're going to talk about the controller. So we've closed our loop for our stabilization. Now we're going to focus on the controller. How do you compute an output based on the error that we measured? And this is what you do in ENE 432, and this is going to be a lot less painful than that. So you're welcome. So PID control. So we're gonna sort of set up our problem that we're going to solve here. One second, excuse me. So you guys can see in my other screen here, I have this 1 degree of freedom test stand, and what 1 degree of freedom means is it can only move in one direction, and that direction is about rotating about this axis. So we're building this model. We define what positive roll is. We're going to say we're stabilizing on angle set point. So we want to tell this thing to go to an angle, and we want it to go there and stay there. Our control output will be the thrust of each motor. Oh, hi, Josh Piccoli. And we assume that our thrust increases linearly with motor speed. Now, this isn't necessarily true, but with PID, it'll sort of just ignore that, and it'll take care of it anyway. And then we assume we always know the exact angle and angular rate from the onboard IMU. It's not going to be exact. There's going to be some noise, but we can assume it's exact and do pretty well. So very first step in implementing PID control is compute your error. So you get your pilot command, the angle desired, and you subtract out the measured angle from the IMU. Next, we're going to add proportional control. So proportional control means that you calculate an output proportional to the error. And all that means is you take the error and you multiply it by some gain KP, that we'll call it. And basically what this means is that, if there's a disturbance or if there's an error, we're going to actuate our motors proportional to that. And then we're going to assign, some baseline throttle to the left motor plus the output, and a baseline throttle minus the output that we've calculated here. And that's going to give us proportional control. This is what the response would look like. Not too pretty. So in orange is our set point. That's what we're trying to stabilize on. And in blue is the response that we would probably see with just a proportional controller. And the reason it looks so bad is because we start here, and then the step response starts, so that the step input starts, and we measure this error, and it's very big, so that the output is very big because it's proportional to the error. So the output's big. We send the outputs to the motors. It creates a control moment, and the thing starts spinning, or it starts rotating, and it starts building up momentum, right? And as we get closer, we pass the set point. We have momentum. At the set point, the error is 0, our output is 0, but we still have momentum. So we just keep going. We pass it. And then we get overshoot, and then rinse and repeat. You do that and you oscillate, and it's terrible. And there's still some steady state error. Now, if there's no damping at all, and when I say damping, I mean energy dissipation from friction, air resistance of the thing, then it will oscillate forever like a sine wave. In this case, there's some damping from the friction that I've coded in to the simulation. So there is a little damping that's settling this, but it's still a bad response. So we're going to go to the next term in PID control, the derivative term, which is basically calculate an output proportional to the derivative of the error scaled by a gain KD. And in a real system, differentiating the error is going to be changing its sign a lot. And it's just going to be noisy because the IMU reading is not perfect. So it's going to be really noisy. So instead, we'll use what we call derivative on measurement. And that means that you take the derivative of the angle instead of the derivative of the error. And if you've taken calculus, you know that the derivative of an angle is an angular velocity. And we have an IMU that can measure that directly. So we're just going to use the raw gyro data for the derivative term. And we'll multiply that by some gain that we can tune later. Note it's negative because basically the derivative term is going to act against the speed of this to prevent those oscillations. And this is what the response would look like. So you can see increase in KD brings down those oscillations. And what's happening is basically that error happens when the step input starts. The proportional term gets really big and it starts accelerating it towards the set point. But the derivative is measuring the speed at which it's going toward that set point. And it says, no, like you're going too fast, back off a little bit. So you subtract off that from the output and it prevents it from overshooting. It prevents it from building too much momentum. And you can see we still have some steady state error here at the end. And this is going to be from, inaccuracies in the test stand. So there might be a mass offset. There might be an external force, so that the proportional and derivative term are just settling on a different set point rather than what we're actually looking for. So that's when the I term comes in, the integral term. And basically we're going to successively add or integrate the error scaled by some gain Ki. And all that looks like is you have your previous integral, so the previous one you computed, plus the error for this time times the elapsed time. That's all integration is. So inaccuracy in the setup, will lead to steady state error that integral term will accumulate on and correct over a longer period of time. One important thing when you're implementing this yourself is you have to saturate the integral. Otherwise, if there's any small error and the vehicle is just on the ground, for example, the integral term will just keep winding up because it's just accumulating this error, and eventually your motors are going to turn on when they shouldn't be turned on. So you have to saturate this term. That just means you set a limit for it to prevent it from spooling up past that. So here's the response with the full PID control. And you can see increasing KI here brings down the steady state error, but you can also see with too high KI, you'll get some new overshoot, and that's integral overshoot. And that's sort of, it brings in the game we got to play with, how do we tune this so that we get the steady state error to go to zero really quickly without introducing too much new overshoot. It's a bit of a trade-off, but that's fine. But basically what's happening here is, we've detected this error between where we are and where the set point is. The proportional term is doing its thing. The derivative term is acting against the speed to prevent proportional from building too much momentum. And the integral term is measuring this error, and it's just adding it, adding it. So by the time it gets to here, when it crosses the set point, there's a little bit too much integral and it overshoots a little bit. And eventually, this error is small, so it slowly brings it back to the set point. So I would say that the yellow here is probably the best tuned out of all of these, the yellow line. This is just a more fancy way of explaining what I just explained. You might see block diagrams like this, but this is the exact same implementation. Basically, your set point comes in and you sum it with your output to get your error. You compute your P, I, and D terms, you sum them, and you send that to your output. That's how this block diagram works. So a general tuning strategy, and you guys are gonna probably employ this if we play around with the MATLAB script I gave you guys, but generally you wanna start increasing your KP in increments of about 10% of some max, and the max is typically specified. It's sort of dependent on the implementation. It's a little weird, but do that until you get some steady oscillations, and then you need to increase KD in about 10% increments to dampen those oscillations. And then finally, you can start increasing, or not finally, but next you can increase KP and KD together, adjusting appropriately to reach your desired response time. So a really low KP and KD will be a really, really slow to respond controller. So ideally you want one that responds fast. So you'll increase these together. If the system is overdamped, it'll be very sluggish and slow to respond to the set point. And if it's underdamped, you'll see those oscillations. So that's where you sort of tune in the KD, the derivative gain. And then finally, to get rid of any steady state error, you can increase KI, the integral term, in increments of about 10% until that error goes to 0. And you want to try and avoid that integral overshoot I explained, which, if too much integral can even lead to low frequency oscillations, which is a whole nother bad thing. Now, I showed you guys simulation for an ideal case, but in the real world, you're going to see something like this. It's going to be really noisy and gross and a little difficult to tune. So your response time is going to be limited by your loop rate. The faster, the better, but if your loop rate isn't fast enough, you're not going to be able to respond very fast. There's noise in the IMU data. The less you can get, the better, cleaner signal. There's control lag. So computing the control output takes about 10 microseconds. Sending that output to the actuators takes 250 to 1,000 microseconds. The actuator is actually responding. It depends on how big they are. The bigger they are, the longer they take to respond. So there's a lot of time between when you compute what you want to send to the motors and when it actually happens. So that leads to some error. And of course, your actuator saturation limits. So you can command that your aileron deflects, 90 degrees. Well, that's not very good, but that's not going to be a very good controller. You're kind of limited by the amount of control authority you have. So what people do is if they don't like their response, they improve their hardware. Improving any of these things will improve your response, or you just tune your gains as best as possible and you deal with it. That's what we're going to do today. There's a third option, which is, we're talking about conventional PID, but there's many ways to write a controller, even a PID controller. This is a little more complicated PID controller that I've written. We're not going to touch this, but basically there's an outer loop that stabilizes on the angle with P and I terms, and that requests an angular rate from an inner loop rate controller that is stabilizing on an angular rate set point. So this has feedback of the rate, and this has feedback of the angle, the measured angle. This gives much better response. If you have any questions about it, I'd be happy to explain later. But you're not limited to just basic PID. You can implement the same idea many different ways. Obviously quadcopters fly like this. You measure the angular velocity or the angle, and you command the motors. You can also use PID for something like altitude hold on a helicopter. If you can measure the altitude with a distance sensor, then you can command the throttle using PID to give you an altitude set point. If you have a rocket and you want it to follow a trajectory, you can program in the set point that you want along the flight, and you can have PID follow that set point to maybe pitch the rocket over. And then maybe, airplane cruise control at a velocity set point. If you measure the airspeed with a pitot tube, you can change the throttle with PID to cruise. So that's just some applications of PID control. Of course, we're using it for stabilization. So now I'm going to talk about simulation in MATLAB. The reason we need this is because we're using a closed loop feedback for our controller. So we can't find an explicit or exact solution for our system. So if we have a differential equation that describes the motion of our system, of our quadcopter or our test stand, we can find an exact solution for that. But we can't apply feedback to it because the feedback is dependent on the state. So we need to use a numerical method to simulate the response instead. A numerical method basically just means we're going to step through time in very small increments, and we're going to find the approximate solution at each time step. And this allows us to add our external disturbances or forcing. When I say forcing, I mean, our computed output for our controller, and we can add that at any point in time along the solution, which is really cool. The Euler method of integration is the simplest, and that's what we're going to use. You guys, this is where you're going to want to pay attention, because I think in ENE for something vibrations, this is a homework assignment. They ask you to implement the Euler method of integration. So hang on to this. We're going to start with a simple pendulum. Here's the equation of motion. Equation of motion is just a second order differential equation. And what we're going to do for the Euler integration, I'll show you guys this in code. Well, you first initialize a time array with some very small dt. The smaller the better, but you run into accuracy limits with your computer. And then you specify your initial conditions. So for a pendulum, we're going to be solving for the angle theta. So we need to specify theta and theta dot. And then we're going to start stepping through time in increments of dt. So for each increment, we'll call each increment indexed by I. First, you're going to solve the differential equation. So we've solved the differential equation for theta double dot, which is equal to a function of theta, theta dot, any constants, any external forcings. Keep a note of that. So there's that. That's simple. You plug in your equation. And then we integrate for theta and theta dot. So the next theta I plus 1, the next one, is going to equal the current one plus the angular velocity theta dot times dt. That's just integrating, right? Accumulating. And then the same for theta dot. The next theta dot is going to be the current one plus the angular acceleration times dt, right? So that the next time that we come around and go in this loop again for the next dt, these theta and theta dot of I plus 1 have already been computed. And that means this theta double dot of I can use them. And that's how you solve a second order differential equation numerically. There's other, there's ODE45 is a popular solver, and they do a similar thing, but they do variable time steps, and they sort of do backtracking to make your solution more accurate. This is close enough. This works pretty well. So now I'm gonna hop over to MATLAB, and I'm gonna show you guys how to do this for that pendulum example, and we're gonna generate the response. So if you guys have MATLAB open, that'd be great. You can code along with me. I'm gonna pause share for a second. Make sure nobody else is in the waiting room. It looks like we're good. Okay, so let me pull up MATLAB here. Okay. One second, guys, sorry. Okay, so I'm going to try and tailor this for everybody here. So I know we have people that are underclassmen all the way up to seniors. So I'm going to try and be nice to all of you here. If you've never used MATLAB, that's fine. Basically, I have a new script that I've saved to my desktop in a folder. One thing when you run MATLAB scripts, you got to make sure that you're in the right folder. So here I am. So if I type pendulum down in the command window, it'll run the script, and there's nothing here. So first things first, we're just gonna hold off, clear all, close all. That's just pretty standard stuff. Next, we're gonna go ahead and define some physical constants. I'm kind of cheating here because I have some code that I'm copy and pasting, but for the pendulum equation of motion that I showed, you need g, gravity, and then you need some length of the string. So any constants pertaining to your particular solution would go there. Now you need some simulation parameters. So t end, I'm just going to say, I want my simulation to run for 10 seconds. So I've just said t end. And I've specified a dt. This is the time step that the Euler integration is going to use. So this is really small. I could go for some more zeros, but then you run into very slow running code. I found this, this amount for this example is acceptable. You'll have to play around with it. And then we create our T array, which is just from 0 to T end in increments of dt, right? So the next step before we actually hop into our Euler loop is we have to define our initial conditions, right? So I'm going to say, paste them, boom, some theta that we're solving for and some theta dot that we're solving for. Our initial condition for theta is going to be 45 degrees. It's arbitrary. You can, depending on your problem, you have different initial conditions. I've said this is 45 degrees, and theta dot is going to start off at 0. That's just where you can specify it. So now we're actually going to hop into our loop where we're going to loop over our equation of motion and solve it for each time step. So I'm going to say for I is equal to 1 to length t. This gives you looping through the entire T array. We're going to integrate the equation of motion that we've specified for the pendulum. So I'm going to paste it here and I'll explain it. So theta double dot, we've solved our equation of motion for theta double dot of this loop iteration is equal to negative g over L sine theta, theta of I, right? Because theta is going to be an array that pops out. That's the pendulum equation of motion, right? So next, we're going to go down and we're going to say theta of I plus 1. The next one is going to be equal to the current iteration plus theta dot of I times our dt. Remember, we specified our dt up here. And that's integrating on theta. And then we're going to do the same thing for theta dot. Right, so theta dot of the next iteration that we come through here is going to be the current theta dot plus integrate, so theta double dot times dt. That's all integration is. And when you do this, because you're doing this I plus 1, you're going to have arrays that are 1 bigger than your T array. So you need to actually get rid of the last index. It's sort of just an afterthought, but it's fine. So we just say the last one is empty for theta and theta dot. And that's it. This will solve for the pendulum equation of motion. So I'm going to actually plot, I'm going to paste in some stuff, but I'm going to plot the angle, and we're going to look at what the angle does for this equation of motion. And if you're new to MATLAB, plot, you just specify your figure. We're going to plot T and theta. Theta is the array that came from our Euler integration. And then I'm just adding some labels here. So save that. I'm going to run pendulum and we're going to see if it throws an error. It didn't. So we can check this to see if it's right. So we said our initial condition for theta was 45 degrees, right? Oh, look, time 0, 45 degrees. Okay, so we're on to the right thing. And if this is just a pendulum in a vacuum, it should oscillate forever. We see it's oscillating, there's no damping. And it, conservation of energy tells us that if we start at this height on one side, it should go to the same height on the other side. So we get a 45 degrees here. So this is the correct solution. You can also plot the angular velocity and acceleration. We generated those arrays as well. I just pasted those in here. Let's see what those look like. They're both going to be sinusoidal, but phase shifted, so that's fine. This is the angular velocity, so here's our initial condition 0. So does anybody have any questions? This is a pretty simple numerical solver here. Anybody? Okay, so what I'm going to do, stop share for 1 second. I'm going to share this script in the chat real quick. So if you weren't following along, or maybe you didn't copy all of the code, I'm going to share this. I would highly recommend holding on to that, and when you have a future homework, you can send me an email and say thanks, Nick. But yeah, ODE 45 is generally what we typically use. It's an integrated solver in MATLAB, much higher accuracy. This is more for specialized cases. So I'm going to hop back in to my presentation here. Here we go. So now we've done the numerical simulation. Now let's apply it to our test stand, right? So first we have to build our equation of motion. And if you've taken 301, this should be a piece of cake. This is a pretty simple example, but if you haven't, I'm sort of going to explain how you arrive at an equation of motion. So here's a test stand. The motors are located at distance r from the rotation point. We've defined, what is positive roll. And we're also going to say that there's some damping here from friction. This is important because we're trying to model the real system. So I've actually tuned my damping coefficient here to my real system. And it's negative because it's acting against the roll. We also have mass on both sides, and that's acting down. So this is our force vector for the weight of each motor, and we're going to ignore the weight of the actual stick. We're just going to take into account the left and right side, which can be different, and they will be. The left motor has an output which is perpendicular to the stick thing. The right motor has the same thing. So to derive our equation of motion, we're going to start with basically Newton's second law, except for angles. And what that is the sum of the moments is equal to the moment of inertia times theta double dot. If you're doing a linear problem, then this is the equivalent to F equals ma, right? Sum of the forces is equal to the mass. Inertia is basically like a rotational mass times a, an acceleration. This is an angular acceleration. So this is rotational F equals ma. So now all we have to do is sum up all of the moments acting on this system and solve for theta double dot. So yeah, this is scary, but I'm going to step through it. So the first moment is going to come from the left motor acting at a distance r. So it's the thrust vector is oriented perpendicular, and it's always perpendicular because it's fixed to this rotating teeter-totter. And that's going to create a positive moment. So R times the thrust of the motor output. Likewise, for the right motor, it's going to be R times the motor output of the right motor, but it's going to be a negative because it's going to want to roll this against positive roll. Then we do the forces from the weight. So the left motor has some weight, and it's located at a distance of R, but we have to take the cosine of that because it's always pointing down, right? So we only want the horizontal component. And it's negative because it's pulling down. It would want to make this roll negative. Same thing for the right mass. Finally, we add that negative C times theta dot. That's just damping. So it's some damping C proportional to your angular velocity. That's just a damper. I'm going to rearrange this and solve for theta double dot. And this is our equation of motion. So if you had any trouble following that, and because you haven't taken a dynamics class, don't worry. But this is something that you will get really familiar with, and I'm sure if you have taken dynamics, this was a very simple example. So in any case, this is what we're actually going to simulate now, and this is accurate. This will work. The only difference is we're going to do it in my MATLAB simulation script, which we use the Euler integration to solve our equation of motion. We're also going to have a PID controller inside of that solution loop that's generating a control moment at certain intervals. And then we're going to play with tuning the PID controller. We're going to tune the test stand. So as we discuss, feel free to tune the PID controller gains in the script that I provided. It's called WIA flight controller or something like that. Those parameters are at the top of the script, KP, KI, and KD. And if you get some good gains to tune, you can give them to me at the end, and we'll upload them, and we'll test them on the stand, and we'll see how accurate our simulation is. So let me hop back over to MATLAB. Any questions so far before I hop into this? Okay, I'm going to share the file one more time for anybody that may have just popped in, but yeah, wiafc.m. So if you want to open that in MATLAB, and then I'm going to share my screen and I'm going to walk you guys through what's happening in this code. So same idea as this pendulum example, except there's some extra things. So I just have our controller gains for the PID controller I implemented. Keep note of like the maxes, because there is a max that I can upload before it gets dangerous. And then keep note of the increments as well. These two guys are just sort of Boolean operators. If it's set to true, then it'll use control delay. So I've implemented a simple control delay based on, the motors take time to spool up. So we can't immediately create a moment. The moment has to be offset by some time. If you set that to true, it'll use it. If you set it to false, it won't, which is fine. And then IMU noise. I've implemented IMU noise. So basically our measurement that the PID controller is getting is not perfect like it would in the real world. If you set both of these to false, then you get a basic PID simulation. With them true, it models this guy pretty well. So I've established some test stand physical constants. These things are all different. The mass of each motor, and I also have an offset mass taped onto this test stand, so that we're gonna need the integral term, right? And then I've tuned the C, the damping term, and the moment of inertia. I've actually just experimentally determined those based on the free response that I get when I let this thing rotate on its own. I set an operating condition of just some baseline throttle that I'm going to be commanding for both motors. And then we talk about some, we add some simulation parameters. So I'm going to do this for 40 seconds. I have a loop rate. The PID loop rate is set to 20 Hertz, which is low, but it's basically throttled by how fast I can talk to the motors. So don't worry about that. And I just have some noise parameters. And here is the time step that the Euler method is going to be using. And then here is the time step that the controller is going to be using, 1 over the loop rate, right? Inverse frequency. And basically, you want your Euler loop to run as fast as possible to get an accurate solution. But the PID loop has to run at a different rate. And I'll show you guys how to do that, because the PID loop is constrained by your physical hardware. I've set my initial conditions, theta and theta double dot at 0. And then here is a pretty simple, I'm creating a step input array for my PID controller. Basically, we're going to be going between 0 and 20 degrees. And here I'm just creating an array of length t that has a step. So for time less than 18 seconds, the desired angle is 0. For time between 18 and 23 seconds, the angle desired is just 20 degrees. And then the rest is going to be 0 as well. We got to initialize some things here, and then we can begin our simulation loop. So similar to the pendulum example, for I is equal to 1 to length t, we're looping over all of the time to solve the Euler. Ignore all of this for now. Ignore all of that. That's my PID implementation. But boom, here's what we just did in the other script. This is just the Euler integration for our equation of motion. And this is the guy that we just derived. And this is identical to the pendulum example that we coded, right? So now we're going to talk about the PID implementation, which happens inside the Euler loop. So we want to run the PID controller at the specified loop rate, right? We don't want it to run every time for every Euler time step, because that's too fast. It's unrealistic. So if the current time minus the time measured at the end of this loop, I just do that here. If the current time minus the time from the previous loop is greater than or equal to the specified controller loop rate, or the specified controller time step, then we can go in and compute our controller output. Otherwise, we just skip over this and we just run the equation of motion, the Euler method, a bunch of times. So only periodically does this happen in the loop. Here I'm just, this is where I talked about the IMU noise. So if we're using the IMU noise, then I just add some Gaussian Gaussian noise to the measured angle. which would be the integrated angle and the angular velocity. These are exact from the Euler method. And the angle, equivalent angle measured as if this was a real system is with noise. And here is the actual PID controller implementation. So we talked about this in the presentation. Here's our error, angle desired minus angle measured. Proportional is just the error. Derivative is negative angular velocity measured from the IMU. Integral is the previous integral plus error times dt controller. And the PID output is going to be the sum of all three of these times their respective control gain. And these control gains are what we're tuning, right? Here is just kind of like an abstract thing. You need to scale it to prevent saturation. And this is sort of at the discrepancy of whoever implements the controller. This is just a scale factor used within the controller that I'm using for the test stand. So this is sort of why all PID gains are kind of scaled differently depending on what software you're using. Don't worry too much about it. And then we do our control mixing, right? So we have a stabilized PID output for our rotational axis, but there's a left motor and there's a right motor, right? So the left motor will get some throttle that we've commanded, so some percentage of throttle plus the PID output. And this is scaled to our maximum thrust. Don't worry too much about that. And the right motor is minus, right? So they act differentially to create one net moment. And this is where I'm just using the control delay. So if we're using control delay that we've defined, then the motor output is just going to be some previous output, 1,000 iterations back. That's just a delay. If we're not using that, then it's just the one calculated at that step in time. And then I bound it. And all this means is that, our motor output cannot be less than 0 and it cannot be more than the maximum thrust that the motor can generate, right? So that's a constraint on how fast our system can be tuned. And then we're done. So we take T controller at the end so that we can monitor this to hop in a loop again. And we basically just integrate our equation of motion. Oh, one last thing. So basically, if you're not running the PID loop for this iteration, then you just want to use the previous PID output, right? You haven't computed a new one, so just use the previous one. And then integrate, and then I just do a bunch of plotting. So let's take a look at, I'm gonna set these to false, so we have an idealized PID case. Are there any questions, by the way, on the implementation here? So if there's no questions, then I'll just sort of play with this a little bit myself before opening up the floor here. But I turned off control delay, I turned off IMU noise. It's just a simple case. Let's set the gain, the KP gain to like 0.3 and run this. Right, so there's our oscillations. We clearly need some damping, right? So I'm gonna put in some damping. It says increments of 0.1 is appropriate, so I'll start with 0.1. Still too many oscillate. Oh, sorry, that was KI. Sorry, I wanted KD. Ignore me. Damping. Okay, so those oscillations are gone, and it looks pretty good. But there's like some steady state error, right? And that's just because there's a mass offset. So if we put in a little bit of integral term that accumulates on the steady state error, boom, it's gone. So we get a little bit of the integral overshoot. But now you can notice, this is kind of a slow response. This is not very well tuned controller. So you can keep increasing the control gains until you bring this this response over to the step that you're commanding, and you get it really close, right? But in the real world, you have control delay, and in the real world, you have IMU noise. So let's see what this looks like now with those. Oh, okay, it's pretty gross, right? It's actually a pretty good response. these gains still need some work, but you might notice though, we can go, we want this, we want to improve the response. So, okay, let's increase KP and KD to bring this this response delay down. So we'll go to like KP 0.5 and maybe KD 0.15 or something like that. Uh-oh, what happened? This would work if we weren't using the control delay or the IMU noise. But what happened? Well, because there's control delay, you're trying to respond faster than you can actually update your controller. And now we get some weird oscillations, and that's bad. So you're actually constrained by how fast you can run the loop rate. So there is a limit on how high your gains can go in a real system. An idealized system, they can go to infinity, and then you basically have an exact step response. So with that, I mean, I hope you guys have been able to run the script and play with it. If you guys have any control gains that you've tuned, I would love to take them now and show you guys what that looks like on this test stand here. Or any questions as well. We can open up some discussion now.
Why did you choose to use MATLAB rather than like C++ or something?
MATLAB is just, I'm comfortable with it. It's in our curriculum. So you could very well do this in Python. I've implemented the controller in C. That's Arduino, and that's what we're going to run on the test stand. So yeah, anybody have any gains we can upload? I'll share my screen here. I'll show you my Arduino sketch that has this implemented that we're going to run. I'm just going to scroll down in my code, and we're going to be adjusting the roll angle, the roll angle gains that I have. Let me power this up just so it's waiting on us. And you guys can, I have two webcams open. 1 second. So if you want to just select the one with the test stand on here, that way you get a bigger view. But okay, somebody give me some gains. Let's do this. Before I have to start doing it myself. Anybody? I'll actually.
You just use the ones that you showed before. I don't have anything new yet, so nothing good.
Yeah, I'll do the ones. What do we say? Like point. Okay, let's do some like really bad ones. Okay, these are intentionally bad. Yeah, this is really sluggish, very low gains. So what I'm going to do is upload this to my test stand. All right, we're uploaded. Gonna let it boot for a second. This, I don't know what these gains will do. They might just oscillate and break something. Should be kind of funny. Okay. All right, so here we go, spinning up. Yeah, so we have some oscillation here. It needs more damping very clearly. Yeah, so not very good gains. If anybody has anything better, I'd love to try it. I can also show you guys the response in real time. So if you're looking at the shared screen instead, here's what the real-time response. Red is going to be the desired, and yellow is going to be the measured from the IMU. So what it's actually doing. You can see those oscillations there. Oh god, too much. Yeah, so it just oscillated itself out of control there. So
would there be an algorithm you can run that just finds the best gain values for you? Is that a thing?
you could. There are called they're PID auto tuners, and basically what they do is they sort of start with a general set of gains that might be good, and then they test a step response in flight, and they can measure the overshoot, and they can adjust the gains accordingly. I see gains. Thank you, Sam. What do we got? 0.3 kp, 0.2 ki, and 0.14 kd. Thanks, Sam. All right, let me upload. And also, if you guys have like stupid gains you want to try, we can do that too. We don't have to do correct gains. Okay, we're uploaded. I'm going to pull up the response here. Okay, ready? All right, pretty steady, and you can see it's pretty much at the set point. I'm going to give a step input. Not bad. So I'll say that this response looks like it's a little bit overdamped. So maybe the simulation is a little bit off. This might have looked like a better response in the simulation, but it seems a little overdamped. So maybe we'll back off on this. Oh, we have another chat. Yes, okay, thank you, Frederick. I'm gonna put your gains in. So we got 0.45 kp, 0.15 ki, and 0.1 kd. Let's see what this one looks like. Sorry, I'm just waiting for the flight controller to boot. Okay, let's try this. Ready? Okay. Okay, so that one I would say was much more responsive, a little bit underdamped. So my only adjustment would be probably adding about 0.02 to KD, and we can look at it again. But yeah, increase in KP gave it a lot more control authority there. And keep in mind we're kind of limited by our control delay and our error and our IMU estimate. So we're really playing a game of trade-offs here. Oops. Okay. So I've increased the damping a little bit because we saw some oscillations. Still better. Yeah, a little better. And of course, with a real system, where there's some slop in the test stand, so it's oscillating a little bit because of that. And that was a pretty good response. So maybe let's set Ki to 0, and we can see what the response would look like. Let's see the steady state error in real time real quick. right, it's uploaded. I'm just gonna wait for the flight controller to boot. And if you guys can see on board this test stand, on the top right corner, that's a Teensy 4.0. It's basically a souped up Arduino, stupid fast. In the center, let's see if I can move this in a little closer. In the center, there's the IMU that's mounted with some foam tape to reduce vibrations. And then the other two little guys are my receiver that is talking to my radio controller. And that's what I'm doing. I'm using to send commands to it. So yeah, so the I term is now 0. So let's see if we can look at the steady state error, because I intentionally put a lot of weight on this side. Let me bring up the plotter. There's still some oscillations there. That's all right. Actually, not too much steady state error, which is nice. So yeah, it's tough to see. So in the real world, steady state error will, if you're flying a quadcopter, it will reveal itself in the form of the quad wanting to drift around a lot, because the set point, or sorry, the steady state error is just off, a couple degrees, and then the quad will want to drift around. So if anybody else has any other games they want to try, we can do anything here. If anybody has any questions, this 000, I love that. You're memeing on me now. Yeah, so 000 would do nothing. There would be no control output, so the motors would just respond to throttle. I would have to do some different control mixing to map to my, directly to my stick on the transmitter, so it'd be completely unstabilized. But I'm gonna share really quick in the chat one more thing, and this might be useful for any of you working on UAVs, or anything that flies and needs stabilization. Or we got another. Oops. Oh, Brandon's got one. I'll upload that in a second. In the chat, this is just my GitHub with all the code. This is the same code that's running on this test stand. It works a lot better on real flying vehicles, not crappy test stands that are kind of thrown together. So things do fly very well with it. You're free to use that, modify it however you need for any projects in the future. Let me upload Brandon's here. What do we got? Oh my gosh. Hold on. Sorry. KP.45, KI.125, KD.1. Let's take a look at that one. So any of you working on, unmanned aircraft, or working with Dr. Paley, the AMAP team, or anybody have any experience working with equipment like this?
I did a little bit my freshman fall for ENA 100.
Right, the ENA 100.
Yeah.
How was it? Were you like flying and tuning and?
Yeah, we used a Pixhawk and then Q ground control, and then we had to figure out how to work with position hold and then altitude hold using our different sensors and stuff. So
right. Cool. Yeah, the position hold works on. I think they use a PD controller in Pixhawk, but I could be corrected. Here's Brandon's gains. I'm going to spin up. follows it pretty well. Yeah, so step response is always going to sort of excite some nasty behavior on a real system, but it follows the a smooth input pretty well, and that's basically what a pilot would be giving it anyway. So this would fly pretty well if it was a quadcopter. So with that, I would of course, any questions, if you guys in the future you're working on MATLAB integration like I've done here for simulation and you need some help, feel free to reach out to me. I'm always willing to help. If you're working on a unmanned vehicle project and you need help tuning your controller, go ahead and send me an email. I love this stuff. I do it for fun. So yeah, don't hesitate to reach out. I will put my email here in the chat one more time. There we go. And don't hesitate to reach out. And thank you guys for coming. I appreciate it. I think we're pretty much done here unless anyone wants to hang out. And thank you. In case anyone wants to hang out, ask questions, nerd out a little bit about off-topic things, I'm happy to stay here. But thank you guys.